Okay. In the last lecture, we learned about the definition of canonical transformations and how to obtain these transformations from generating functions. The idea of generating functions to get the canonical transformations is of course slightly awkward, because for a given transformation getting generating function is still slightly harder, but if I am given a generating function, getting canonical transformation is very easy. Okay. Now, what we are going to do in today's lecture is we are going to try and obtain a direct condition to test whether given transformation is canonical or not. Now, before that, this condition is called a symplectic condition. So, before I derive that condition, what I will do is I will put our Hamilton's equations in what is called as a symplectic notation. Okay. So, let us start doing that. First, I am going to introduce this idea by taking few examples, very simple examples. Take a system with 1 degree of freedom, okay, with 1 degree of freedom. So, your canonical variables are 2, I will denote them as q and p, and the Hamilton's equations. So, the Hamiltonian of course is function of q, p and t, and the Hamilton's equations we can write as q dot is equal to partial derivative of h with respect to p, and p dot is minus partial derivative of h with respect to q. Okay. What I am going to do is I am going to put this in a matrix form. So, first thing we will do is define a new variable, a matrix variable, which I will write as eta, and in this eta the first entry is q and the second entry is p, okay. And then dp d eta by dt, this would simply become q dot and p dot. So, this is what will go to the right side of the equation, left side of the equation, and to the right hand side we have. So, I will define this operator del q. This operator is also a matrix operator, I will put it in the matrix form. So, on the first one you write del over del q, and the second one you write del over del p. The order of q and p, remember in our entire structure we keep q first and then comes p. Okay. So, I will put it in that order. Now, I will write down the Hamilton's equations. So, Hamilton's equations will look like equations will be eta dot, that is d eta by dt, and this must be equal to q dot p dot, but from the Hamilton's equation I know that this is equal to del h over del p, and this is minus del h over del q. Okay. Rewrite this as a product of two matrices. So, this will be 0 1 minus 1 0, and here I will write this as del over del q, del over del p, and acting on h. Okay. Let us put everything together. So, call this matrix as a J matrix. Okay. This is your some sort of a gradient matrix. So, we have eta dot is equal to J, then gradient acting on H. Okay. This is the form in which we want to put the Hamilton's equation. So, this is a matrix equation. This is matrix equation in 2 by 1 matrices. Okay. Okay. Let me take one more example just to make this idea even clearer. Let us take an example with 2 degrees of freedom. Now, I have 4 canonical variables. I will put them in this order q 1, q 2, p 1 and p 2. Okay. And then write down the same trick. you put these variables in a matrix form. On the right hand side, you have partial derivative of h, you also put that in the matrix form, keeping the order of the variables same as the first one. Okay. So, I will write eta as q1, q2, p1 and p2, and in that case eta dot will become q1 dot, q2 dot, p1 dot and p2 dot. Okay. And now I am going to put this in a matrix form. On the right hand side, I want to do this. I want to keep that gradient matrix with a proper order. So, this will be partial derivative with respect to q1, partial derivative with respect to q2, partial derivative with respect to p1 and with respect to p2, and this operates on h. And what is the structure of this matrix here? This will be your 4 by 4 matrix. What would be structure of this matrix? Remember, this is very easy to guess, but I will write it as blocks of 2 by 2 matrices, and if you put all the entries there, it looks like this. So, it is 0 0 0 1, and on the lower side you have -1 -1 0 0 -1, and you can very quickly verify. Look at this, q1 dot here will be equal to partial derivative of h with respect to p. Okay. So, that settles it. So, the structure of this matrix is important, because this is what will appear in your general case. So, finally, again we can write eta dot as the matrix J. Remember, now it will be 4 by 4. It is 4 by 4 because you have 4 canonical variables, and gradient with respect to eta of h. Let us put this in. Let us write the same equation for the general case. In the general case, now you have n degrees of freedom. That means you have 2n variables, and these 2n variables would be q1 to qn, and then you have p1 to pn. So, how do we construct our eta matrix? Very simply, eta matrix is nothing but a matrix where you have q1 all the way, and then there will be n q entries, and then remaining n entries will be in terms of p1 to pn, and then your gradient matrix in the same way, that will be partial derivative with respect to q1, and it will run, the first entries will be partial derivative with respect to q1 to qn, and the remaining entries will be with respect to the canonical momentum. So, del Pn. So, this is the del matrix. The interesting thing is, of course, the structure of the J matrix. Okay. So, here also equation will turn out to be eta dot will be equal to J eta h, and the structure of J matrix will be something like this. J matrix now of course is 2n by 2n matrix, and in this 2n by 2n matrix I will divide this into 4 blocks of n by n matrices. So, what goes here, I will denote it as 0 matrix, identity matrix. In the lower side you have minus identity matrix and a 0 matrix. Okay. 0 matrix is the one where all entries are 0, and identity is of course we are familiar with. So, the structure of this J matrix is something like this. Now, here these equations in the matrix form are called as Hamilton's equations. in symplectic form. The reason for this nomenclature is this. Look at the properties of J matrix. Now, properties of J matrix are one, first of all, irrespective of what is the size of that, remember it must be 2n by 2n. So, its order is even. So, J square is quite clearly minus I, and remember this I of course is 2n by 2n. J transpose and also equal to J inverse, this is equal to minus of J. This is very easy to see. If you look at the structure of the J matrix, it is antisymmetric, okay? And then a simple calculation there will verify that J inverse also must be equal to J transpose. And finally, you have determinant of J is always equal to plus 1. All these are easily verifiable properties there. Now, if you take a arbitrary matrix, if M is in this case 2n by 2n matrix, such that M J M transpose is again equal to J, then this matrix is called as symplectic matrix. Then M is called as symplectic matrix. We will make use of this definition of symplectic matrix in a moment. And then of course, you can also see that identity is symplectic. For every symplectic matrix, there is an inverse matrix which is also symplectic, and so on. So, basically the set of symplectic matrices forms a group. Okay. So, we will explore that in a moment. So, this is the Hamilton's equations in symplectic form. Okay. Now, let us apply this to the problem of canonical transformation. And here in the problem of canonical transformation, what I am going to do is this. I am going to first restrict ourselves to the transformations which do not depend on time. So, the specific kind that we are looking for here is, say you have the old variables which are p and q, and then you want to make a transformation to the new variables which are capital Q and capital P. Okay. So, this should be Q first and P later. Okay. And these transformations are special in the sense that Qi, these are functions of old variables, but not of t. Remember in the first section when we defined the canonical transformations, we did not put such a condition. These transformations could depend on time t, but right now I am going to just focus on these ones. So, capital Pi is also a function of q and p, and because they do not depend on time t, these are also called as restricted transformation. So, restricted, and if these transformations are canonical transformations. Okay. Now, let us see. Let us put this in the proper form, in the matrix form. So, your eta is of course a column matrix containing q's. So, q1 and all the way up to Pn, and the new variables I will put them in a matrix and call them by the name xi. So, xi contains capital Q1 all the way up to capital Pn. Okay. Now, let us see how does this work. So, clearly if I want to calculate xi dot, so if I want to take d by dt of xi, Remember, xi contains capital Q and capital P, which in turn depend on small q and small p, but all that will go inside the new nomenclature of xi and eta. So, this would be sum over j. So, I will take one component of that matrix, one element of that matrix. So, this will be partial derivative of xi with respect to I and eta j and then d eta j by dt, okay. And then you recognize this matrix. What is this matrix? Oh, this is nothing but the Jacobian of your transformation. So, if these are the transformation equations, then the Jacobian, I will define it as M matrix whose ijth element are given by del psi I by del eta j. Okay. This is one. Now, on the right hand side, we require the gradient transformation. So, gradient with respect to eta, if you take ith component of this, then it is nothing but derivative, partial derivative with respect to eta I, and this I can write it as sum over j del xi j eta I and del over del psi j, okay. And this we will write it as sum over j. Now, this is m j I. So, that would be del with respect to xi and this would be jth component. Okay. So, now I can put this in neat matrix form. What happens to d by dt of eta? This is nothing but matrix M times d psi by dt. Okay. So, the other way around, d psi by dt is M times d eta by dt. But what happens to the gradient operator in the matrix form? So, the gradient with respect to eta is, notice that now what you are getting here is m j I. So, I want to write this as m transpose times gradient with respect to xi. Okay, this is what we want. Right. Now, let me put this in Hamilton's equation. In the Hamilton's equation, remember you have, so the Hamilton's equations would be eta is equal to j times with respect to eta, derivative with respect to eta of h. Now, you pre multiply both sides by matrix M. So, you have M eta dot is m j and the gradient with respect to eta can be now written as m transpose gradient with respect to xi h, and you immediately recognize that m times eta dot is also equal to psi dot. Okay, great. And this, if you compare, so if the transformation was canonical, then what we expect is this xi dot must be equal to j times gradient of this if the transformation is canonical, and then you compare these two and say that the transformation is canonical if M is symplectic. Now, we are using the definition we wrote in the previous slide. So, canonical if and only if, you can see that the only if part would also be very simple if Jacobian matrix is symplectic. Okay. I will give you one analogy of this. Remember, I was talking about the Newton's equations. Newton's equations are left invariant by special kind of transformations which only rotate the Cartesian coordinates. And what kind of matrices are those? Those are called as orthogonal matrices. So, Newton's equations are invariant under the orthogonal transformations. Here the Hamilton's equations are canonical if the Jacobian matrix is symplectic. So, this has a similarity with the idea of form invariance of a particular set of equations. Okay. I will immediately apply this to some examples. So, if I take first example as an identity transformation. Okay. So, in identity transformation you have capital Q I must be equal to Q I and capital P I must be equal to P I. Okay. So, this is identity transformation. In terms of eta, of course, these are again Q1 to Pn and xi is nothing but Q1 to Pn. And what does this transformation tell you? That this transformation essentially says new variables are exactly same as old variables. And what is the Jacobian matrix for this? So, Jacobian matrix ijth element is nothing but xi I eta j, and this is nothing but delta ij. What does that mean? That means Jacobian matrix in this case is identity matrix. So, Jacobian matrix is identity matrix, and we already know identity matrix is also symplectic by the definition of symplectic matrices. So, this transformation is canonical transformation. We already knew that from the first lecture. Here is a second example. This also we had done it in the previous class. So, this is the transformation where you interchange momenta with the coordinates. So, all the Qi's will become old Pi's and all the momenta will become minus of Qi's. Okay. Now, what is the Jacobian matrix of this? Can you see that the Jacobian matrix of this is in fact nothing? If I write it as 4 blocks of n by n, then Qi, its derivative with respect to small qi, the partial derivative, that is 0. So, you would get whole of this 0 n by n here. What about Pi's? Pi's partial derivative with respect to small pi, that is also 0, which means all these entries here are also 0. And then the what goes here is basically here are the entries which are partial derivative of q with respect to p. So, that would be I n by n, and that minus sign will give you I n by n here. Oh, this immediately tells you that this is exactly equal to your J matrix there, exactly equal to J matrix, and J matrix is symplectic by itself. Okay. So, one more example. This is the example we had already seen again. So, this transformation is capital Q. I will just stick to 1 degree of freedom for this example. So, capital Q is small q cos alpha minus small p sin alpha, and capital P is q sin alpha plus p cos alpha. And what is the Jacobian matrix for this? That is again very simple. We can straight away write down just by inspection, because there are only 2 variables there. So, this would be cos alpha minus sin alpha and cos alpha. Can I ask you people to verify this now, that m j m transpose, this would be equal to this matrix with entries cos alpha minus sin alpha. I am writing this in a shortcut. So, sin alpha, cos alpha, and then you have 0, 1, minus 1 and 0, and then remember it is a transpose now. So, it will be cos, sin, minus sin and cos. Simplify this, it is simple product of 3 matrices and show that this comes to the J matrix again. Okay. So, this transformation is also canonical transformation. I will do one more example, the example of harmonic oscillator. Okay. So, here the transformations are, so your old coordinates are q and p, new coordinates are capital Q and capital P. So, the transformations are small q is equal to square root of 2p by m omega times cos of capital Q. So, what we are writing here is actually inverse transformation, but does not matter. You can also think of this as a transformation from canonical variables with capital Q and capital P to the new variables which are small q and small p. Okay. Now, p is square root of 2 p m omega into sin of capital Q. Take this, construct the Jacobian matrix. Now, it is not as simple as the previous examples, but it is straightforward again. So, in the Jacobian matrix what we get is partial derivative of q with respect to capital Q, partial derivative of q with respect to p, then partial derivative of p with respect to q and partial derivative of p with respect to capital P. I will write down all these entries here, but I am going to leave the actual calculation of m j m transpose equal to j to you people again. So, the partial derivative of q with respect to this would be minus square root of 2 p by m omega into sin of q, then this would be 1 over square root of 2 p m omega into cos q. Okay. This is the derivative of this. Now, for the capital Q, this will be square root of 2 p m omega into cos of q, and finally, here you have square root of m omega by 2 p times sin q. Okay. So, this is your Jacobian matrix, and now you just put it back into the symplectic condition and see whether this transformation is canonical or not, and you will find that this is actually a canonical transformation. Okay. So, all this while what we were doing was to try and apply this symplectic condition which we derived for restricted transformation. But of course, I also want to go and see what condition I would get if I, instead of restricted transformation, start using general transformations. It turns out that the condition is in fact exactly same. Even for the general transformations, the general transformation will be canonical if and only if the corresponding Jacobian matrix of the transformation is symplectic. But you see, the proof that we have here will not work. It will not be as simple as the proof which we have done. You can immediately see, I can show you the steps where here. So, if I am looking for transformations which are general in nature, then your transformations here will also be functions of time t. Now, if they are functions of time t, you see what happens here. This is a step which would fail, because the transformations here are themselves functions of time t. That means, when you take d psi by dt, now you have an additional term there, and once you have that additional term, this proof will not go through as is. The right hand side of the equation will still be there, but the left hand side will not work. Okay. So, the normal proof for this kind of transformations is tough. What we will do, we will try to do it in slightly different way. This is the treatment which is given in Goldstein's book. So, I will be following that treatment straight away here. So, what I am going to do is, first of all, I will introduce a notion of infinitesimal canonical transformation. So, infinitesimal canonical transformation. So, you have your original set of canonical variables, which is qi and pi, and you want to map them to capital Qi and capital Pi. And in this case, we will not assume that the transformations are restricted, which means capital Qi, these are functions of q, p and as well as t, and capital Pi are also functions of q, p and t. The only thing that I am going to assume here is that it is an infinitesimal transformation. That means, the new set here which I am going to denote by the matrix notation psi, and the old set here eta, they differ by only an infinitesimal. That means, xi is equal to eta plus some small deviation delta eta. Okay. So, there is a identity transformation, we are very close to the identity transformation, the change that will happen will be very small. Okay. So, let me start doing this. What kind of generating function would give me a transformation like this? So, if I take the function, generating function of type 2, type 2 remember is a function of small q and capital P, and we of course are going to assume that this is also function of time t. Okay. Time t, and this one here sum over I q I capital P I. So, if I just keep it to this, I get an identity transformation, because capital Q will be equal to the partial derivative of f2 with respect to p, capital P, and that will give you small q I. So, this will give you identity transformation, but what we want is q, p and t. So, I am going to add another function g and multiply it by an infinitesimal epsilon. Okay. So, epsilon is infinitesimal number, so that the change is minimal. And what kind of transformation it would generate? So, if I for example, look at capital Q I, this will be equal to partial derivative of f2 with respect to P I, okay. And this immediately gives you Q I plus epsilon times del G over del P I. Okay. And for the other one, capital P I, the small p I will be equal to del of f2 with respect to q I, and this will give you capital P I plus epsilon times del G over del q I. Okay. Now, this gives me delta q I, which is epsilon times del g by del pi. Okay, this is capital Pi. What is delta q? Remember, it is a new value minus the old value. So, this is in fact capital Q I minus small q I. This thus. Now, you look at this differential here. The capital P is related to small p through a linear equation, and to the first order they are equal, or 0th order they are equal. The first order already has an epsilon, and then you have epsilon sitting here. So, if we want to just keep the terms in epsilon, I can also write this as del g over del small p I. Okay. And similarly, capital P I minus small p I, this will be equal to delta p I, and this will be equal to minus epsilon del g by del q I. Okay. All right. Now, look at these two equations. I can put them in the matrix form again. So, delta eta, this is nothing but in the matrix form you have delta q 1 all the way going up to delta p n. Okay. And those are exactly the equations or quantities that we have gotten here. So, your delta eta will be equal to, and look at the structure of this. This is going to be epsilon times j because of p here, q here, and into, so del eta of g. So, the change in eta in this infinitesimal canonical transformation is given by epsilon times j times the gradient of g with respect to eta. Okay. Now, what is the Jacobian of this matrix? The Jacobian of this matrix, Jacobian matrix of this transformation I can write this M, matrix M, which is nothing but del. So, if I take ijth element of this is del psi I by del eta j. But we already know this is nothing but, so if you write it in full matrix form, this will give me M, which is epsilon, so identity plus epsilon times j times, then you have g. Okay. To be careful, I will again rewrite this. What does this matrix mean? This is again 2n by 2n matrix. Remember, this ijth element of this. So, g ijth element of this matrix is nothing but second derivative of g with respect to del eta I, del eta j. Okay. So, this is your matrix of Jacobian matrix of the transformation. Now, what is transpose of this? Transpose of this, you can see identity matrix here is symmetric. What about this matrix? This matrix is also symmetric by the definition of this. Remember, we are going to assume G is sufficiently differentiable and is continuously differentiable, which means the order of the derivatives do not matter, which means this matrix is symmetric. So, all that will happen is when I take the transpose of this, it will be minus epsilon times j g. Okay. And now, let us apply this to, or let us put this to test. So, the symplectic condition says check for M J M transpose. but this is nothing but identity plus epsilon times j times second derivative of G, then J matrix, and then there is a I minus epsilon J G. Expand this, throw away epsilon square terms because the second order terms, we are only looking at infinitesimals. So, this is nothing but the first term you get is J. What do you get next? It is epsilon J, then this matrix into J, but you get the same term from the other side with a minus sign, and that is how you get 0 and then terms which are second order. So, you see, even for a arbitrary transformation, I mean not restricted transformation, the symplectic condition holds, but for the infinitesimal case. So, infinitesimal canonical transformation, or I will write this as infinitesimal transformation is canonical if and only if Jacobian matrix is symplectic. Now, we are getting somewhere, but see, this is only true for infinitesimal case. Now, how do I go from infinitesimal case to a transformation which travels over a finite time difference? So, what you do is this. Now, I will write this here. You start with eta, okay, and then you make a transformation to xi. But the transformation to xi depends on not just eta, but time t. Okay. So, what you do is this. This transformation, let at t is equal to 0, you have xi eta t 0, I will call this as xi 0. Okay. So, you have one transformation from eta frame or eta set of coordinates to xi 0. At some other later time at t is equal to t 1, then call this as eta even, call this as xi 1. Okay. So, after time t you have a transformation to xi 1. Now, if I look at this as a transformation from this is time axis, this is t 0 and this is t 1. So, what you do is this, you divide this t 0 to t 1 interval into small sections there, each of time duration delta t. Okay. And now, think of it like this, you go from xi 0 to xi 1 in series of infinitesimal steps, and every time you take a infinitesimal step, you go from xi 0 to xi 0 plus some delta xi. In the next step, you go to xi 0 plus delta xi 1 plus delta xi 2. So, like this you would be making several steps, but what is the transformation between xi 0 and xi 0 plus delta xi 0? It is canonical if the transformation matrix is symplectic. So, you can think of transformation from here to here is canonical if individual infinitesimal transformation. So, the total transformation is in fact product of all these infinitesimal transformations, and then remember the condition for symplectic matrices too. So, what will happen here is the Jacobian matrix of the total transformation also will appear as a matrix product of the individual infinitesimal transformations, and then if the individual ones are symplectic, the total product is also symplectic. That is how you go from here to here. xi 0 to xi 1, okay, and ascertain that the transformation between xi 0 and xi 1 is canonical. And then you can look at it like this. You are going from eta to xi 0 and then you are going from eta to xi 1. Think of it like this. So, it is a product of, so eta to xi 1 is basically product of going from eta to xi 0, which is canonical, and this one is canonical because individual infinitesimal transformations in between, they are also canonical, and hence the condition, symplectic condition, holds for any transformation, which means any transformation would be canonical if and only if the Jacobian matrix is symplectic. It does not matter whether Jacobian matrix is time dependent or not, which means the transformations are time dependent or not. Okay. In the next class, we will look at what remains invariant when you have a canonical transformation.